Okay, so we're heading into the home stretch. Chapter 9.1 is about hypothesis testing. This is the theoretical part of it. So there's a lot of text, not a lot of math. So while there's a lot of slides, I may not do a lot of talking about it. So what are hypothesis tests and how do we do them? So a hypothesis is a claim. All right, and so we're either talking about the proportion, population proportion, or population mean, and we're trying to say that there's something about this, and we're going to test this claim with some math and come up with some values to decide, whether the claim is valid or not. So here's an example. So we have a company, and they're called ProCare, and they have a product called Gender Choice. And what it is it's a product that will allow you to determine to take it if you want to have a girl or a boy. And so they've taken it and they give it to 100 parents, and they looked at the women, the children, and they found that they assumed they should get about 50-50 for boys and girls. But if it works, they should get significantly more girls than boys. And so what's important is what's significant. Well, we always know from previous chapters that 5% is very important, and that 0.05. There's also significant of 0.01. But if we're doing medical testing, we're really interested in that 0.01 level of significance. But other things were is 0.05, and so we can use both of those to determine whether this is successful, and we'll look at it, how it works. So we're going to do this hypothesis test and say, well, gee, is the fact that we get 64 girls out of 100 births significant? And so we have to make some assumptions. And the first one is that it didn't work, that the product doesn't work at all, and so we should get a 50-50 split for probability. But if it does work, then we look in our sample here, and we got 64 births out of 100, and we do find the likelihood of that occurring. So is that significantly more than 50%? And we have to create tests where we have a standard, and then we have to see, well, what's the other choice going to be? So if we find that the 64% is unlikely, then we can conclude that yes, the product did actually work. However, if the 64% is able to happen by chance, then the product wouldn't have been effective. So and here they're saying we're not proving that the product isn't effective. We're just proving that it is not effective, whether or not it's not effective. And because like they're saying here, there may be other explanations. Okay, so we're just testing our theory about whether this works, and then we would continue to test it again and again and again. It's really what's happening here. So when we have our test, we have to have two choices. Remember, we always have probability has it happened and it didn't happen. Those are A and not A. So we have that it works on raising population, from 50%, and that it doesn't work of raising the population by 50%. So those are the two things we have to deal with, and we have to put them into some kind of category so we can actually test them. And so we have what we call the null hypothesis. And the null hypothesis is that there was no change. So the null hypothesis here is that the population proportion was 50%. So that didn't work. Nothing happened. The alternative would be, well, gee, if it worked, we would have something that would come out bigger than 50% in this case. So that's our alternative hypothesis. okay, is that it's larger than 50%. And we can have a couple other alternatives we can use. I'm going to show you in a second. We have either that it's less than, greater than, or not equal to, because sometimes we are interested in, can it be on either side. So depending on what we're testing, these are going to be the three alternatives that we have: less than, greater than, or not equal to. And a less than test we call left-tailed, because we're interested in the values being smaller on the left-hand side of the normal curve. We have the greater than, which is right-tailed on the right-hand side of the normal curve. And we have not equal, which is two-tailed, because it can be on either the left or the right-hand side of the normal curve, and in those extreme areas. Our null hypothesis is always going to be equals. Okay, that's it. There's always just equals, because that means it's set equal to the normal standards that we're expecting. The population mean that we've determined, this is the value that we're looking for. Okay, we're looking to see, have we changed it at all from that? So those are your two things. You're going to have your null hypothesis, which is always just going to be equal sign, and your alternative, which is going to be less than, greater than, or not equal to, depending on what you're looking to find. So here's some examples, and they just want you to identify the parameter which we're going to claim. So we're going to make our null hypothesis and our alternative hypothesis. And when we do our alternative, we're going to have to say whether it's going to be left, right, or two-tailed, depending on whether it's less than, greater than, or not equal to. So we have a manufacturer of a hybrid car, and they advertise that the fuel consumption is 62 miles per gallon on the highway. And the consumer group says that no, it's less than that. So they've made this one very easy for us. Our population parameter is mu, because we're not dealing with proportion, we're dealing with average. Okay, we have our mean value. So mu is equal to 62. And because the group was saying, well, no, it's less than that. Well, because they said less than, well, we know we're going to use the less than sign. So the less than sign is going to be, our alternative is going to be mu is less than 62 miles a gallon. Okay, which means that this is a left-tail test, because we're looking at value, we're only interested in values that are going to be on the left side of the mean. So that one was set up very nicely for you. The next one here says the Ohio Department of Health says that the average stay in hospitals after childbirth is greater than the national average of 2 days, 2.0 days. Again, very easy for us. We know we're dealing with population mean, because mu, because they've said mean in it already. And we know that we're going to have a right-tailed test, because this is greater than. So our null and alternatives are going to be H0, which stands for null hypothesis. Mu is equal to 2.0 days. And our alternative, because they wanted greater than, is mu is greater than 2.0 days. And because it's greater than, we have a right-tailed test. So in this last one, we have a biologist who's looking at the proportion of female zebras in the region. And he wants to know if it's different from the expected proportion of 50%, because they assume there should be half and half. So here we're talking about proportions, so we know we're going to have P. Okay, and we're dealing with P is equal to 0.5, which is 50%. So our null hypothesis is that P is equal to 0.5. Now, because they said that we're different, they don't care if it's greater than or less than, it's just not 50%. So that's why we have different is going to give us not equal to. So the alternative is that P is not equal to 0.5. And because we have not equal to, we have a two-tailed test. So that's the first part of setting up a hypothesis test, is figuring out your null and alternative hypotheses. Okay. Then we have to figure out, well, how do we determine if we can, which one is right, which one we go with, null or the alternative. And so we have two outcomes that can occur. We can either reject the null hypothesis and say, well, no, that's not correct, or we can not reject the null hypothesis, which says that, well, we don't know, we don't have enough evidence to support the alternative. Notice we're not accepting anything. We're either rejecting the null hypothesis and we have enough evidence to support our alternative, or we are not rejecting the null hypothesis and we don't have enough evidence to support the alternative. We're never accepting the alternative, and we're never accepting the null hypothesis, because we don't have enough information on this one test to do that, and we can never actually ever accept the null. We can never prove that something isn't there. We can prove that we can very easily see something is there. There's a chance of this, but we never ever accept the null hypothesis. We just either reject it or do not reject it. Okay, those are the very important things to keep in mind. So, and here they're going into this. Notice accepting the null hypothesis is not an outcome, because that's always our starting assumption. And the hypothesis test only gives us reason to either reject it or not reject it. Okay, we can't ever conclude that the starting assumption is true. Alright? So that's a very important thing to know. And we always formulate our hypotheses before we take our samples, because otherwise we may be drawn to a certain answer before we formulate our questions. So we want to formulate our questions first, then sample it and test. Okay? Because if we do it afterwards, we may be getting into trouble. So here they're going to do those hypothesis tests again. Alright, but now we are going to have a value that we're going to be able to say, well, gee, can we reject this or not? And so here we have our mu of 62 degrees, and our mu is less than 62. And our outcomes are that we are going to reject that mu is equal to 62 miles per gallon based on the evidence. Or we are not going to reject the null hypothesis based on lack of evidence to support the claim. Okay, so neither one of those allows us to imply that the advertised claim is true, because it's a sample. We didn't look at the population. We looked at a sample, so we can't claim that the 62 miles per gallon is true. We can just claim that we don't have enough evidence to reject it. The next one, with the stay of 2.0 days for Ohio, we can either reject that it's equal to 2 days, and so we have enough evidence to support the claim that the stay is longer than 2 days, longer than the national average, or we cannot reject the hypothesis, and so we don't have enough evidence to support the claim. But again, we never said that it is equal to the national average, because we could actually be less than 2.0 days. So we don't have evidence to support the claim, but that doesn't say that the claim is true. Okay. And the last one, we had our 50% population of female zebras, so we can either reject the claim that it's 50%, and so we have evidence to support that that is wrong, or we cannot reject the null hypothesis. Okay, but we again don't have information to accept the 50%. We just don't have enough evidence to support the claim that it is not, that we can't reject it. So here Levels of significance. Now we know what we're going to do with those claims. How do we get there? Well, we look at the zero point 0.01 level of significance, which is very strong, and the 0.05, which is moderate amount of evidence. Okay, because I mean, remember, 0.05 is really 2 standard deviations away. 0.01 is 3 standard deviations away. So if we're more than 3 standard deviations away from the mean, we have very strong evidence. If we're 2 standard deviations away, but not quite 3, we have a moderate amount of evidence. You know, we still are willing to reject the null hypothesis on certain things, but if it's a medicine, we would rather have the 3rd standard deviation. But we have a moderate amount of evidence to reject that claim at the 95% level, or you know, the 0.05 level of significance. Okay, so if it is bigger than 0.05 and 0.01, then we don't reject the null hypothesis. Okay, depending on which one we're looking at. So if the p-value, the probability is bigger, is 0.0582, we would not reject the null hypothesis at the 0.05 level of significance. If the probability was at 0.046, well, we could reject it at the 0.05 level of significance, but not reject it at the 0.01 level of significance. So, depending on what we're looking at and how much level of significance is what we're whether we're going to reject or not reject. And so again, they go back to these problems. So here we have our fertility probability again, where we're trying to get females, and they did their hypothesis test out, and they found that the probability of getting 64% of the of a random sample to be female was 0.0026. So they want to know, should we reject or not reject the null hypothesis? And at the 0.0026 level probability, well, we can reject it. And here they're saying it's slightly under 3 per 1,000 chances. So we could reject at the 0.01 level of significance, which also means we could reject at the 0.05 level of significance. So we have significant amount of evidence to reject the null hypothesis, and that supports the alternative that it does raise the proportion of girls that are born. Now that probability we call a p-value. Okay, and so when we have a small p-value, less than 0.05, then that is unlikely to occur because you've got less than a 5% chance of occurring by chance. We use that. If it's less than 0.05, we reject at the 0.05 level. If it is bigger than 0.05, then we do not reject. Again, they're saying the same thing. They're just giving it a new name. That probability we've now called a p-value. Okay, that p-value is the same numbers that we looked up in Table A under the normal curve. So full circle, we've come back to that. Okay, so do we have a fair coin flip? And here they're saying, well, we flip a coin 100 times and we got 40 heads. And again, we do our calculations and we get a p-value of 0.0228. Well, can we say that that coin is fair or not? So a fair coin would be that the probability occurs 50% of the time. The alternative is here that we're saying that it is not fair. Okay, so we have fewer heads, so it's less than 50%. Okay, so when we look at these, we look at our p-value, we got our p-value of 0.0228, and we compare that to the 0.05 level of significance. Well, 0.0228 is smaller than 0.05, so we can reject at the 0.05 level of significance. But it's not less than 0.01, so we do not reject at this level. So we can say that there is statistical significance at the 0.05 level to reject the null hypothesis conclude the coin may be biased against heads. So that's all that we've done. We've just taken our test, we've taken found our null hypothesis and our alternative hypothesis. We took our p-value, compared it to our level of significance, and made a decision. So those are the steps. Step 1. Figure out what your null and alternative hypotheses are going to be. Are you doing mean or are you doing proportion? Do it before you grab a sample. Okay? Step 2. Grab a sample. Alright? Find that statistic that you're looking for. The mean, the proportion. So, then do a z-test. Okay, determine the likelihood. They haven't told you how you're going to do it yet, but you're going to do a z-test. Determine the likelihood of getting at that sample. So find your p-value. Then compare that p-value to your level of significance and decide whether you're going to reject or not reject the null hypothesis. Okay, one more test. One more example here. We have a car company. He has 12,000. They want to see, well, are these cars driven 12,000 miles per year? And he got a sample of 225 cars. And he found the average distance that these cars were driven was 12,375 miles. So, what is he going to do in his hypothesis test? So, step 1. He's got to figure out his proportion, his population parameter. Well, he was talking about mean. Okay, the mean was 12,000 miles. That's the national average. He wants to know, well, what's his fleet doing? So, the null hypothesis is that the mean is equal to 12,000. The alternative is that the mean is bigger than 12,000. Okay, or greater than 12,000. It's a right-tailed test. He's only interested in, does the numbers come on the right side? Because if it's less than 12,000, he's very happy. So now we have to do our calculations. We have to figure out a way to use this. So he took a sample, and he had to get a sample of 225 people, 225 cars, and he found a mean of 12,375. Now, step 3. Find the value. Okay. And so he does his work. We want to find the probability of getting a sample mean of 12,375 out of 100 cars. And it says they don't need the calculation because we're told that the probability is 0.01. Right here. In our problem. We found that the fact that getting is at least 0.01. So, we have a p-value of at least 0.01. Okay. Now, next step, we compare it. So, we have a p-value of 0.01 that tells us it's significant at the 0.01 level. So, we can reject the null hypothesis that the mean is 12,000. We have enough strong support, significant evidence to support our claim that our mean is actually greater than 12,000. We can reject the null hypothesis. That's what we did. Sorry. And here's our another one I didn't delete, but the null hypothesis. Remember, we're innocent until proven guilty. So the null hypothesis is always the defendant is innocent. The alternative is that you are guilty. So, and that at certain levels we need to be more sure than at others. For a murder trial, we probably want to be sure at the 0.01 level of significance. Whereas if it is a financial claim, we might want to only be sure and certain at the 0.05 level of significance. Okay, so we have to look at those things, and we can put them into that kind of an analogy. It's just trying to give you an idea. Okay, this is the basis. We are all innocent. The alternative is that we are not innocent. So that's it.